Let me talk about the basic unit of quantum information, a quantum bit, which we also call a qubit. In these lectures, I'm going to use, whenever I want to refer to a qubit as a physical system, I will draw this diagram. It's just my own symbol for a physical qubit, where the two lines here, you may think about them, or I think about them as kind of energy levels of a two-level atom. Of course, there are no two-level atoms in nature, but what we are talking here about is that we have a complex atom. We just select two levels and label them. Label them 0 and 1. So this physical system, and of course there's much more to it, but this simple physical system that has two energy levels or two quantum states that we can reliably distinguish, and we call one of them 0 and the other one 1. That is our basic unit of information, of quantum information, called a quantum bit. And whenever I want to illustrate the processing of quantum information, then I'm going to draw what is called a circuit or a network diagram. So the qubit will be represented by a horizontal line, and I will put boxes on this line. So I will label them as A, another box B, another box C. So this diagram represents a sequence of elementary operations that perform on a qubit. You know, this is a logic gate, a quantum logic gate, which is characterized by a matrix, right? So we know that one way to describe quantum operation is just to tabulate all probability amplitudes involved in the transition when the qubit goes from here to here. So there's operation A, followed by operation B, followed by operation C. Of course, these matrices are not just any matrices. In order to be consistent with probabilistic interpretation of probability amplitudes, they have to be unitary matrices. So A and B and C are unitary matrices, and we know that the overall operation, the result of A, B, and C is another unitary matrix, which is the product of the three. And do remember, we write them in the reverse order. So U is equal to C times B times A. So unitary matrices, the definition or the property, defining property of a unitary matrix is U times U dagger is equal to the identity. They, of course, form a group, and that the group operation is just matrix multiplication. So we call this group U2. So a set of unitary matrices 2 by 2, and the group operation, as I said, is the matrix multiplication. Now, of course, one qubit is not enough. We will start with one qubit, but in order to talk about any meaningful computation, we'll have to have many more than just one. So you can think about a certain number of qubits. Let me just draw 3 of them. So that those are my two-level atoms. And we can just prepare this input, say 0, 1, 1. So this one is in state 0, this one is initially in state 1, and this one is also in state 1. And again, a network will be just illustrated by a diagram where, again, each horizontal line will represent a quantum bit, a qubit. And when I want to specify any interaction, either on individual qubit or on a pair of qubits, then I will just write a box which will represent a quantum logic gate. So for example, I just may have one here, A, then I may have another one that involves 2 qubits, B, and as we are progressing, we may have another one, say here, that also involves 2 qubits, and then say some operation, call it D and E and F. So clearly A will be a 2 by 2 unitary matrix, B will be 4 by 4 unitary matrix, C will be also 4 by 4, it involves 2 qubits, right? And D and E and F will be 2 by 2 unitary matrices. So in general, if I have n qubits, then the number of configuration that I will have is of course 2 to the n, right? So the first qubit, we have 2 states, 0 and 1. 2 qubits, we have 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. And in general, for n qubits, we will have 2 to the n different elementary configurations or different basis states. So altogether, we will be dealing with the group which is u 2 to the power n. So the overall matrix that acts on the diagram or on a circuit that involves n qubits will have a size, will be just 2 to the n times 2 to the n matrix. So it's a huge matrix. But the whole art of quantum computing is to construct those matrices out of very simple units. So like here, A and B and C. And we will be playing only with matrices that involve at most 2 qubits. Well, sometimes maybe 3. But as a matter of fact, we will show that in order to build any matrix, any unitary matrix, all we need are just very simple unitary matrices that involve interactions on 1 qubit or perhaps 2 qubit interacting together. So single qubit gates and 2 qubit gates would be just enough to construct any unitary operation or any number of qubits, as long as we just can somehow figure out how to build up a sequence of gates so that they just give us a desired unitary transformation. By the way, when we deal with quantum circuits or networks, I should say that some people say this diagram is a quantum circuit and some other will say this is actually a quantum network. Usually the European or the Oxford way was calling this quantum network, but over time everyone started calling it a quantum circuit, so you know, I'm just giving up. Call it as you wish, call it a circuit, call it a network. As long as it is clear what you have in mind, that's fine. So a quantum circuit has at least 2 figures of merit that are very important here. When you describe a quantum circuit composed out of simple elementary gate, you refer to its size by saying, by counting the number of gates. So the total number of elementary gates, which we fix later on, will be called the size of the circuit. And so in this particular case, for example, we have 1, 2, 3, 4, 5, 6 gates. So the size of the circuit, size in our case is 4. And then we also talk about the depth of the circuit. And the depth is roughly the number of computational steps or time steps that you have to perform in order to complete the computation here. And that's different from, of course, the number of gates, simply because some gates can be performed in parallel. For example, this sequence, D and E and F. So the circuit essentially can be, the circuit depth is essentially calculated by slicing the circuit into layers, and so that the gates in each layer can be performed in parallel. So in which case we have how many? 1, 2, 3, and 4. So the depth of this circuit is also 4. So the size of the circuit, I do apologize, is not 4 but 6, and the depth of the circuit is 4. Well, and of course, you know, for computer scientists, what is important is not exactly what is the size or the depth of the circuit, but how does it scale with the size of the input? So how does it scale with n? If we deal with n qubits and we want to construct a unitary operation, what is the number of gates we have to use? Does it scale exponentially? Does it scale as a polynomial function of the size of the input? And what is the depth of the circuit? That is essentially the execution time. That is actually a very important parameter, because the scaling of the depth tells us how many computational steps we have to perform in this circuit in order to get the answer.